Hello again. So, in our previous lecture, we were talking about units of measurement, and I introduced several different physical quantities that we measure in science: length, mass, time, and volume, and their associated SI units. Now, I want to introduce another physical quantity: temperature. So, temperature, you probably have an idea of what temperature is. Technically, its definition is the measurement of heat flow or the measure of energy flow. And we're going to talk about it a lot more when we talk about thermodynamics later on this semester. The SI unit for temperature is Kelvin, not degree Kelvin, just plain old capital letter K, Kelvin. Kelvins are not referred to as degrees. Now, you're probably not used to measuring or thinking about temperature in Kelvin. So, some key conversions to have on hand is that a Kelvin is simply the temperature in degrees Celsius offset by 273.15 units. So, what is 0 degrees Celsius in Kelvin? Well, 0 degrees Celsius would be defined as 273 Kelvin if you plug it into that equation there. So you can see from this relationship that it's really just offset by 273 degrees Celsius versus kelvins. The size of the unit is the same for both Celsius and Kelvin. All that's different is the 0 points. So 0 degrees Celsius is 273 Kelvin, whereas 0 Kelvin is minus 273 Celsius. That temperature is known as absolute zero. Absolute zero is a temperature where molecular motion theoretically would stop. It's never quite been reached in a laboratory environment. It's the 0 point energy from a thermodynamic standpoint, and we're going to define it more in the thermodynamic chapter. So you can convert easily from Celsius to Kelvin by just adding 273 to the Celsius temperature or subtracting 273 from the Kelvin temperature. Now, Fahrenheit is not an SI unit, but it's useful to have the conversion from Fahrenheit to Celsius. And then, of course, you can go from Celsius to Kelvin. If you take a factor of 1.8 and multiply it by the temperature in degrees Celsius, and then add 32 to that, that's a way of transforming a Celsius temperature into a Fahrenheit temperature. You could rearrange that equation to transform Fahrenheit into Celsius. So looking at because of this multiplicative factor here, the size of the Fahrenheit degree and the Celsius degree are different. I guess I should say the sizes are different. So it's not just the 0 points. The 0 points are different too. So are the 0 points. With Kelvin and Celsius, the 0 points were the only things that differed. But here, the size of the degree actually differs. Celsius degrees are larger than Fahrenheit degrees. Okay, so you not only have a different 0 point, you have a different size of the degree. And a great way to illustrate this is to consider one of our favorite substances, water. Water, of course, is the biological solvent. It is the universal solvent. It's a really important substance, and it's also a useful substance for understanding kind of how the Celsius scale came to be. So we have Celsius and Fahrenheit scales here. Water is a substance that, like any substance, undergoes phase changes. So it can go from liquid water to ice. Ice is just solid water. So that's called freezing. It can also vaporize from liquid water to steam. And steam is just the gaseous form of water. Now, the temperatures at which these phase transitions happen are known as the boiling point and the freezing point, respectively, of water. Now, you may know the values of the boiling point and freezing point of water. I'm going to change color just so this is a little easier to read. But the boiling point of water, of course, is 100 degrees Celsius. The freezing point of water, of course, is 0 degrees Celsius. Now, if I use this equation up here to convert those Celsius temperatures to Fahrenheit temperatures, I find that in Fahrenheit, the boiling point of water is the Manhattan area code, 212 degrees Fahrenheit. And the freezing point would be just 32 because of this equation, degrees Fahrenheit for the freezing point of water. You can also try to figure out from the equation where these temperature scales meet. And if you do that calculation, you'll find that at -40, that is where the Celsius and Fahrenheit temperatures actually meet, the one value at which they are the same. So that kind of gives you some kind of quantitative idea. And just by looking at the differences here, you have a 100-degree gap between the freezing point and boiling point of water in Celsius, but that gap is much larger in Fahrenheit because the Fahrenheit degree is smaller than the Celsius degree.